Welcome to the deep dive. Today, we're jumping into something really cool, time travel.
Yeah, it's one of those ideas, isn't it? Shows up everywhere, science fiction, but also, surprisingly, in actual physics.
Exactly. And we know it's something you've probably thought about too. Can we do it? What would happen if we did?
Absolutely. So for this deep dive, we've looked at, well, a whole range of stuff, from the big theories like Einstein's, which sort of set the stage,
Right.
to the more, let's say, speculative ideas about wormholes and things, and even the ethical side of it. It gets complicated.
It really does. So our mission today, let's unpack the most fascinating bits. Figure out what, established science versus what's still way out there.
And maybe see what it all tells us about time itself. It's pretty fundamental stuff.
Okay, let's start at the beginning then. How did we even start thinking about time
Yeah.
in the way we do now? Wasn't it always just ticking along?
Well, for a long time, yeah, that was the view. Think Aristotle, Newton, they saw time as absolute, like a universal clock.
A second here is a second everywhere else.
Pretty much. Independent of space, independent of who's looking, just absolute time. Makes intuitive sense, right?
Yeah, totally. Feels right in our daily lives.
Yeah.
But that changed.
Big time. Early 20th century, Einstein comes along with his theory of special relativity, and one of its core ideas just flips everything on its head.
Which is?
The speed of light. In a vacuum, it's constant. Always the same speed for everyone, no matter how fast you're moving towards it or away from it.
Wait, that sounds weird. If I run towards a light beam, shouldn't it seem faster?
You'd think so, but no, experiments confirm it. The speed of light is constant. And for that to be true, well, something else has to give.
And that something is time and space.
Exactly. They can't be separate, absolute things anymore. They have to be flexible, interwoven. This mathematician, Minkowski, helped formalize it as space-time.
Space-time, like a fabric.
That's a great way to picture it. A four-dimensional fabric where space and time are linked. What happens in space affects time, and vice versa.
Okay, my brain's starting to bend already. So this space-time thing, it has real effects.
Oh, absolutely. The first big one is time dilation.
Right, time dilation. I've heard of that. Time can slow down or speed up.
Special relativity gives us velocity time dilation. Basically, the faster you move through space, the slower you move through time relative to someone stationary.
So like if I was in a super fast rocket.
Exactly. If you zoomed off near the speed of light and came back, you'd find you've aged less than people on Earth. Your clock would literally have ticked slower.
Wow.
Yeah.
Seriously. That's incredible. So you could return and everyone you knew would be way older.
Potentially, yes. It sounds like science fiction, but it's a direct consequence of the constant speed of light and space-time. There's no single universal now.
Mind-bending. Okay, you said velocity time dilation. Is there another kind?
Yep. Comes from Einstein's next big theory, general relativity. This one's about gravity. It gives us gravitational time dilation.
Gravity affects time, too.
Yeah. General relativity describes gravity not as a force, but as a curvature of space-time caused by mass and energy. The more massive an object, the more it curves space-time around it.
Okay.
And the stronger the gravity, meaning the deeper you are in that space-time curve, the slower time passes.
So time literally runs slower, closer to, say, a planet than it does further away.
That's exactly right. Even here on Earth, time passes just a tiny, tiny bit slower at sea level than it does on top of a mountain because gravity is slightly stronger closer to the Earth's center.
That is wild. Are these effects, like, noticeable or just theoretical?
Oh, they're measurable and actually crucial for technology we use every single day. Think GPS.
GPS. My phone navigation uses Einstein.
It absolutely has to. Those GPS satellites are orbiting way up high where Earth's gravity is weaker.
Right, so their clocks should run faster.
Faster, exactly. By about 45 microseconds, millionths of a second per day compared to clocks on the ground.
Okay.
But they're also moving really fast in their orbits.
So velocity time dilation comes back in, making their clocks run slower.
Yep. That slows them down by about 7 microseconds per day.
So you have one effect speeding them up, one slowing them down.
And the net result is that the satellite clocks run faster than ground clocks by about 38 microseconds each day. It sounds tiny, but if the GPS system didn't constantly correct for this difference,
My map would be way off.
way off, errors would build up so fast the whole system would be useless within minutes. It's amazing proof that these relativistic effects are real.
Wow. Okay, so time isn't fixed. It can stretch and shrink. That's already kind of like time travel, in a way. But what about the sci-fi version? Tunnels through time. Wormholes.
Right, wormholes. That's where things get even more speculative, but they do arise as theoretical possibilities within Einstein's general relativity.
So what is a wormhole, according to the theory?
Think of it as a hypothetical shortcut through space-time, a tunnel connecting two different points.
Different points in space, like going from here to another galaxy instantly.
Could be different points in space, yeah.
Right.
Or it could be different points in time. Or both. That's the time travel connection.
A tunnel through time. Okay, that sounds amazing. Is it just math or...
Well, the equations allow for solutions that look like wormholes. The first kind, linked to the math describing eternal black holes, the Schwarzschild wormhole, turned out to be unstable.
Unstable how?
It would basically pinch off and collapse the instant anything tried to go through it, so not very useful for travel.
Ah, so not a cosmic highway then. Bummer.
Not that type, no. But then people started thinking about traversable wormholes, ones that could theoretically stay open long enough for something or someone to pass through.
And how would that work?
That's the big catch. Most theories suggest you'd need something called exotic matter.
Exotic matter. What on earth is that?
It's hypothetical stuff with properties unlike anything we've ever observed. Specifically, it would need to have negative energy density or negative pressure.
Negative energy, like anti-gravity.
Sort of. It would effectively push space-time apart, counteracting the natural tendency of the wormhole throat to collapse. It would prop it open.
And do we know if this exotic matter exists?
We have no evidence for it existing in the amounts needed to stabilize a macroscopic wormhole. Some quantum effects might produce tiny amounts of negative energy, fleetingly, which leads to ideas about maybe microscopic wormholes being possible without exotic matter, but probably only big enough for information, not people.
Okay, so human-sized wormholes are still a big question mark because of this exotic matter problem.
Pretty much. Though there are some even more advanced speculative theories, like certain brain world models where maybe larger ones could exist, but we're really pushing the boundaries of known physics there.
Understood. Still fascinating, though.
Yeah.
Now, you mentioned black holes earlier. Aren't they sometimes linked with wormholes in theories?
Yes, that's another angle people have explored. We know a black hole has a singularity at its center, a point of, well, essentially infinite density and gravity where our physics breaks down.
Right.
One theoretical idea was, what if a black hole wasn't just an endpoint, but an entrance? Paired with a hypothetical white hole, the opposite, something nothing can enter, only exit could they form the two ends of a wormhole.
A black hole entrance and a white hole exit. That's a wild concept.
It is. But much like the basic Schwarzschild wormhole, these black hole white hole bridges, called Einstein-Rosen bridges, are also generally thought to be non-traversable and incredibly unstable.
They'd collapse too.
The prediction is yes, likely collapsing the moment even a single photon tried to enter. There's some thought that maybe spinning black holes might create more stable structures inside, potentially avoiding the singularity, but honestly, our understanding there is very limited.
So it seems like traveling through space-time might be tricky, especially if you want to go backwards.
Yeah.
Which brings us neatly to paradoxes.
Ah, yes, the paradoxes, the classic headache of past time travel.
Everyone knows the grandfather paradox, right? Go back, accidentally prevent your grandfather from meeting your grandmother.
And poof, you're never born. Which means you couldn't have gone back in time to cause the problem in the first place. It's a logical contradiction, a temporal paradox.
Exactly. It makes your head spin. Are there other kinds of these paradoxes?
Oh yeah, there are consistency paradoxes. Generally, any action that would make the time travel itself impossible, like going back and destroying your time machine before you use it.
Right. Okay.
Then there are information paradoxes, sometimes called causal loops or the bootstrap paradox. This is where information or an object seems to have no origin.
Like how?
Imagine you're a fan of Beethoven. You travel back, give him the sheet music for his Fifth Symphony before he's written it. He publishes it. Later, you pick up that published music and travel back to give it to him. So, where did the symphony originally come from?
Whoa. It just exists in a loop.
Exactly. It exists without ever being created. It's not necessarily logically impossible like the grandfather paradox, but it's deeply weird and challenges our ideas about cause and effect.
Definitely weird. So if past time travel were possible, how could the universe possibly deal with these logical knots?
Well, physicists and philosophers have come up with a few ways it might work out. One idea is the Novichov self-consistency principle.
Self-consistency, what's that?
It basically says that the laws of physics will conspire to prevent paradoxes. If you travel to the past, the probability of you doing anything that would cause a paradox is zero.
So you can go back, but you literally can't kill your grandfather. something would always stop you.
That's the idea. Maybe your gun jams, maybe you slip on a banana peel, maybe you just find you can't bring yourself to do it. The outcome is fixed to be consistent with the fact that you exist and traveled back.
Hmm. Does that mean you don't have free will then? If the outcome is predetermined?
That's the philosophical debate. Novikov argued it doesn't remove free will, just that any action you freely choose to take will inevitably turn out to be part of a consistent history. But yeah, some critics feel it's a bit convenient, like defining the problem away without explaining the mechanism.
Yeah. It feels a bit like saying it just works out. Are there other ideas?
There's Stephen Hawking's idea, the chronology protection conjecture. He suggested that the laws of physics themselves might actively forbid travel to the past on a macroscopic scale. He proposed that as you tried to form a path to the past, what physicists call a closed time-like curve, or CTC quantum effects, like vacuum fluctuations, would build up and create a blast of energy that would destroy the path, or the time machine, before it could be used.
So the universe has its own security system against paradoxes.
Kind of like a natural feedback mechanism, yeah, protecting the timeline.
Interesting. Any others?
Well, there's one interpretation of quantum mechanics, the many-worlds interpretation, or MWI.
How does quantum mechanics get involved?
MWI suggests that every time a quantum measurement is made, or perhaps any time a choice point occurs, the universe splits into parallel universes, one for each possible outcome.
Okay. Branches of reality.
Exactly. So if you went back in time and, say, did manage to prevent your grandparents from meeting, you wouldn't erase yourself from your original timeline. Instead, you'd simply create a new branch, a new parallel universe where you were never born. Your original universe would remain unchanged.
Ah, so you don't actually change your past, you just hop onto a different track, a different universe.
That's the concept. It neatly avoids the paradox by saying any change creates a new, self-consistent timeline. Of course, it means accepting the existence of potentially infinite parallel universes, which is its own huge can of worms.
Wow, okay. Lots of ways to think about avoiding paradoxes. Now, we've talked a lot about wormholes and bending space-time. What about just going really, really fast, faster than light? Isn't that linked to time travel sometime?
It often is in fiction, yeah. But here, Einstein throws up another major roadblock with special relativity.
Good kid.
The famous idea that nothing with mass can reach the speed of light, let alone exceed it.
Why not?
It comes down to the relationship between mass and energy. You probably know Einstein's most famous equation conceptually that energy and mass are equivalent.
Right. Energy equals mass times the speed of light squared.
Exactly. What that implies is, as you accelerate an object with mass closer and closer to the speed of light, its kinetic energy increases, and so does its effective mass, its resistance to further acceleration.
It gets heavier.
Effectively, yes. And as you approach the speed of light, the energy needed to accelerate it further approaches infinity. You'd need infinite energy to actually reach light speed if you have mass.
So only things without mass can travel at light speed, like light itself.
Precisely. Photons, particles of light, have no rest mass, so they can travel at that cosmic speed limit. Everything else is stuck below it.
So all those warp drives and hyperspace jumps, pure fantasy.
Well, direct faster than light travel seems ruled out, but there are theoretical loopholes people explore, like the Alcubierre warp drive you sometimes hear about.
How does that supposedly work?
It's less about the ship moving through space faster than light, and more about warping space-time around the ship. It would theoretically compress space ahead of the ship and expand it behind.
Creating like a wave the ship rides on?
Sort of, yes. Creating a warp bubble that moves the ship from A to B potentially faster than light would take through normal space, while the ship itself stays relatively still inside the bubble.
Okay, but is there a catch?
Oh, yeah, a big one. Just like traversable wormholes, the Alcubierre drive, as currently understood, would require vast amounts of...
Let me guess. Exotic matter. With negative energy.
You got it. Same problem. And there are other theoretical issues, too. Another thing sometimes mentioned is quantum tunneling.
Where particles can sort of jump through barriers?
Yeah, they can appear on the other side of a barrier they shouldn't have enough energy to cross. It can look instantaneous, but whether that actually constitutes faster than light information transfer is heavily debated and likely not the case in a way that's useful for FTL travel or communication.
So the universe seems pretty insistent on its speed limit.
It does seem to have some pretty strong rules in place.
Okay, let's step back a bit. If, hypothetically, time travel was possible, especially to the past, what about the ethics? Should we even do it?
That's a huge question, especially if something like the many worlds idea was true, where changing the past creates a new timeline. If you went back and, say, tried to prevent a disaster, are you responsible for the consequences in that new timeline?
Like the classic what if you stopped Hitler scenario. Some argue that could have paradoxically led to an even worse outcome or a longer World War II under a different regime. You just don't know the knock-on effects.
Exactly. The unforeseen consequences could be massive. You'd be playing dice with entire realities.
But what about under the Novikov principle, where you can't change the past? Are there ethical issues there too?
I think so. Even if your actions are predetermined to be part of a consistent loop, you might still inadvertently cause harm. Imagine going back knowing a terrible event happens, trying to stop it, but your actions, despite your intentions, end up being the cause of the event you were trying to prevent.
Whoa. So you become part of the tragedy you're trying to avert.
It's possible within that framework, and it raises questions about free will and responsibility again. If your actions are predetermined, are you truly responsible for them, even if they cause harm? It gets very murky.
It really does. It's clear that time travel isn't just a physics problem. It's a philosophical one too. And of course, it's been a huge part of our stories for ages.
Oh, absolutely. From ancient myths about sleeping for centuries to H.G. Wells' The Time Machine, right up to modern sci-fi films and books, it reflects this deep human fascination with time, regret, hope, and control.
We see all these ideas played out, don't we? Stories about changing the past, the butterfly effect.
Definitely. Or stories exploring stable time loops, where characters are trapped repeating events, like in the bootstrap paradox idea, and countless attempts to imagine how paradoxes might be resolved or avoided. It's fertile ground for storytelling.
So, wrapping this all up, where do we stand on time travel? Is it coming soon to a gadget store near you?
Probably not anytime soon. While the flexibility of time shown by relativity is real and proven,
Time dilation, yeah.
actually traveling significantly into the future is theoretically possible with sufficient speed or gravity, though technologically immense, but travel to the past remains deeply problematic. Wormholes need exotic matter we haven't found, and paradoxes pose major logical hurdles.
So the physics seems to put up some serious roadblocks, especially for going backward.
It does. Ideas like Novikov's principle, Hawking's conjecture, or many worlds offer ways around the paradoxes in theory, but they each come with their own set of assumptions or challenges. For now, it's firmly in the realm of theoretical physics and, of course, imagination.
But even just exploring these ideas, it really changes how you think about time itself, doesn't it?
Absolutely. Studying time travel, even theoretically, forces us to confront the nature of causality, the structure of space-time, and the limits of our current understanding. It pushes physics and philosophy in fascinating directions.
It really does. It makes you appreciate just how weird and wonderful the universe might be. Thanks for digging into all this with me.
My pleasure. It's mind-bending stuff.
And for you listening, here's a final thought to chew on. We experience time as a river flowing in one direction. But given everything we've talked about space-time being interwoven, quantum strangeness, the theoretical possibility of loops, could our linear perception be just a limited human view? Could past, present, and future be less distinct, more connected in the grand scheme of reality than we usually imagine? Something to think about.